Welcome to this explainer. We're diving straight into the incredibly high-stakes world of modern railway system safety today. You know, when you stand on a platform and watch hundreds of tons of steel just effortlessly glide to a halt, you're witnessing an absolute marvel of engineering. But the true guardian of that train, it's not actually the steel tracks or those physical color light signals. It is an invisible web of software and system configuration. So today, we're taking a masterclass on the unseen code and the really rigorous human processes that make those split-second, literal life-or-death decisions across global railway networks. So let's jump right into this wild paradox of modern railway infrastructure, because here's the incredible reality we have to face. The computer systems controlling these trains are so astonishingly complex that they can never actually be 100% tested. Think about that for a second. You simply cannot physically or mathematically test every single combination of train movements, weather conditions, track states, and potential hardware failures. It's practically impossible. And yet, we trust our lives to these systems every single day. So how on earth do engineers solve the impossible? How do you guarantee safety when absolute certainty through testing is completely off the table? Well, here's our roadmap for how we'll figure that out today. 1. The invisible railway guardian. 2. The limits of testing. 3. Configuring the railway. 4. The master blueprint. And finally, 5. Controlling the chaos.
All right, Section 1, the invisible railway guardian.
As passengers, our eyes are naturally drawn to the tangible stuff, right? We see the heavy, physical tracks, the glowing signals, the massive trains themselves. But behind all that heavy hardware are millions of lines of unseen computer code constantly evaluating the state of the railway to prevent collisions. To really grasp this, we've got to define the core concept at the very heart of the railway: interlocking. Whether it's an old-school mechanical system with big metal levers, an electrical relay system, or a modern computerized microprocessor, an interlocking is essentially just a logic machine. Its entire job is to enforce mutual dependency between signaling functions. This means it physically or logically prevents a signal from turning green if, say, the track points ahead are set to the wrong route, or if another train is already in the way. It's the ultimate gatekeeper. And to function at all, it absolutely requires flawless, accurate application data. Moving on to Section 2, the limits of testing. When you're dealing with systems of this magnitude, the idea that a single software developer can just sit down, write flawless, perfect code, and test it once to prove it works, well, that's a total myth. We're dealing with systems that have to account for electromagnetic interference, crazy vibrations, human error, and just countless track configurations. Because end-to-end testing of every single scenario is mathematically impossible, safety has to be built completely differently. It relies instead on robust software production processes and the absolute competence of the engineers designing it. Safety is manufactured through rigorous verification in each and every phase of the development lifecycle. It requires incredibly clear, auditable documentation, exhaustive validation, and constant training and competence testing of the human beings involved. We aren't just trusting the code. We're trusting the highly controlled systematic process that created the code.
Which brings us to Section 3, configuring the railway.
One of the biggest challenges in railway engineering is that you simply cannot build a completely new, custom software program from scratch for every single train station in the world. I mean, it would be insanely expensive and incredibly unsafe to constantly write net new code. So how is a standard software product customized to work safely in a completely unique local location? Think of it like a layered cake. At the bottom, you have the generic product software. This is the basic operating system created by the manufacturer, used universally across all kinds of railways. On top of that sits the generic application software. This contains the specific signaling logic and the broad rules for a particular country or a whole railway network. And finally, the icing on the cake is the specific application logic. This is the highly localized geographical data that configures the whole system for the exact track and signal layout of one specific project or station. So the absolutely crucial point here is drawing a stark contrast between those top two layers. You have the generic application, which holds the universal signaling rules of an entire railway network, rules that dictate general safety principles for everyone. But then you have the specific application, which is the highly unique, customized geographical data. This specific data tells the computer exactly where the curves are, where the points switch, and where the specific signals are physically located on the ground. The system is completely blind without this precise local data. Which leads us to this incredibly powerful quote. The safety of the railway is critically dependent not only upon the core interlocking product, but also upon the correctness of the specific application data. I want you to really take that in. You could literally have the most brilliantly engineered, perfectly verified core software operating system in the entire world. But if a local signal design engineer inputs a track length incorrectly or misidentifies a switch in that specific geographical data, the result is just as catastrophic as a fundamental flaw in the core software itself.
Section 4, the master blueprint. If specific local data is that critical, how do we make sure it never gets corrupted, lost, or misunderstood? Well, this is where we shift our focus away from the software code itself and look at the administrative and engineering protocols. Enter configuration management. Now I know, it sounds like really boring bureaucratic paperwork, but we have to reframe how we think about it. Configuration management is the ultimate defense against chaos. It is the absolute, unquestionable source of truth. It guarantees that every single engineer, operator, and maintenance worker is looking at the exact same accurate baseline of information at any given second. Without it, you don't have a safe railway. You honestly have a ticking time bomb of miscommunication.
Configuration management is built on 4 unshakable pillars. First is identification, uniquely identifying every single piece of information or product so you know exactly what is what. Second is change management, ensuring that every single proposed modification goes through a super strict control process. Third is status accounting, keeping a really clear historical record of what changes have occurred, what's pending, and what got rejected. And fourth is audit and review, physically and virtually checking that the documented rules actually match the real-world equipment out on the tracks. Together, these elements protect the physical and functional integrity of the system throughout its entire lifespan.
And finally, Section 5, controlling the chaos. Theoretical pillars are great and all, but what actually happens in the real, high-stakes world when a piece of hardware fails or a track layout urgently needs an update? It triggers a really rigorous, unforgiving pipeline. Let's say an engineer needs to update a piece of software to reflect a new track layout. Step 1, they must uniquely identify the exact item and document that needs changing. Step 2, that proposed change is pushed through strict change control. That means interested parties review it, assess its impact, and either authorize or reject it. This is what prevents uncontrolled information from causing a literal collision. Step 3, once approved, status accounting is updated so everyone knows the new pedigree of the data. And finally, Step 4, an audit is performed to confirm the system in the field actually matches this new design. A single proposed change has to survive this entire gauntlet.
And let's be real about why this strictness is so necessary. The human element. There is a very real truth in engineering, and just in life. People, by nature, will adopt the path of least resistance. On a super busy railway, there is always immense pressure to deliver a job right now, fix a problem quickly to get delayed trains moving, and promise to just update the documents later. In the long term, that attitude is absolutely deadly. And that is exactly why audits and reviews are so essential. They challenge people to adhere strictly to the process, making sure no one takes a dangerous shortcut.
Which leaves us with this final, really critical thought to ponder. If invisible software is what's keeping the trains on the tracks, who is making sure the source of truth never lies? It's not just the computers. It is the incredibly disciplined engineers, the configuration managers, and the strict safety protocols standing guard. The next time you see a train arrive perfectly on time, I really hope you leave this explainer deeply appreciating the immense, invisible order maintained by these dedicated professionals. Thank you so much for joining me. Keep learning, and I'll catch you in the next explainer.